On recorder. I had to back up, start over. All right, so let's go look at 24 real quick. Just kind of flies by. I didn't quite finish it yesterday, or Monday, excuse me. We'll just kind of pick up here, kind of walk back through it real quick. Maybe answer almost all those questions quickly as we go. Everybody okay? Back up. If you get anything exciting going on, right? Nothing going on. Y'all being very quiet today. Y'all scaring me, man. All right, all right. So anyway, this is actually a pretty cool chapter. And if you go back and I'll get that video up, y'all had a chance to look at it because I haven't posted it yet. But if you remember, I will go back to that same restoration chapter. I mean, the equation I wrote that you need to know. Remember, sugar plus oxygen makes carbon dioxide and water. So basically, we eat sugar and we eat proteins and fats for energy. Those are the three things we get energy from: fats, proteins, and sugar. Okay. And when we Mistress Nick has brought me that pen to my office because she got to her office and she's a collector. Remember, she brought me the pen a while ago. But when we eat protein, which is one of our big sources of energy, all amino acids have a carbon. Oops, come on, don't be like that today. Just freaking work today. Thank you. All right. The amino acids, there are 20 amino acids that make proteins. If you remember, there's a carbon in the middle, and there's a hydrogen stuck on it, and there's this R group that's different for the 20 amino acids. So that's the variable part. Then there is a carboxylic group, a COH, and an amine group, an H2. So I kind of drew it backwards because the end does mine. This ain't nothing but protein chain, carbon chains, right? They go right into the cellular respiration, glycolysis, Krebs, ETS. We have to cut that amine group off, and it becomes an H2. And there's always some hydrogen around, and it grabs it and forms ammonia. And ammonia will kill you. Very deadly chemical. And so the liver takes that ammonia, or this amine group, and carbon dioxide, and makes a compound called, that you all heard of, called urea. And urea is not deadly. And the purpose of the urinary system mainly is to filter out these nitrogen-containing wastes that we make in our body. And the main one, and for which urine gets its name, but it's pretty cool, right, is urea. Okay, really cool. But I didn't know that. I did not know that. I got into the physiology of this. I mean, it's really kind of cool when you put it together. So urine is water, and then urea, uric acid, which is a breakdown product of DNA metabolism, and some creatine, which is a breakdown product of fat metabolism, and a bunch of electrolytes, salts and stuff, right? Sodium, potassium, all this stuff. And we just get rid of the ions we don't need, but the main purpose is to get rid of these nitrogen wastes. And I think I said before to y'all, I think I picked on you, asked him being a basketball player, when y'all eat before a game, y'all would eat a bunch of chicken or meat, and then after the game, your urine is yellow as can be, you smell it, right? Because you've been metabolizing protein. If you go out on Friday night and drink 5 margaritas and a bowl of pretzels, it's going to be clear as water, right? Or beer is clear as water because you become heavy protein. So you're just getting rid of water electrolytes, okay? Pretty cool when you think about it. So this is the purpose of the urinary system, okay? And that's what it's going to say here. So the urinary system controls fluid electrolyte balance, gets rid of metabolic waste, urea, and controls pH and blood pressure by the more you urinate, you let air out of the tire, blood pressure goes down. You don't urinate, you're making water, you're drinking water, blood pressure goes up like putting air in a tire. So very important controller of all these things. The urinary system itself is made up of, actually, hold on, there's more functions. Let's do the functions real quick. So that's the main one controls osmolarity of blood. It controls blood pressure by how much it lets out. It makes the hormone erythropoietin, remember, that is also the hormone that makes the bone marrow make more blood. That is also the first biotech drug for the big pharmaceutical company called Amgen. So in 1993 or 4, they bioengineered human erythropoietin, and it was their first billion-dollar drug. Everybody that has kidney failure, because one of the things that happens when you have kidney failure, you quit making that hormone, then you get anemic, and then it's just like a train wreck. So everybody in America that's having kidney problems takes this drug, and everybody going in for elective surgery, like you got to have a knee replacement, they might shoot me up with this 2 days before, so my red blood cell count will go up, so I'm going to have a unit of blood to 2 units of blood. So it saves a lot of trouble for us having to use less blood. So super big, real famous drug, been out now 25 years, and made Amgen, they give them the money to then become the largest biotech company in the world, or maybe not large, but top 5 anyway. Maybe top 2 or 3, okay? All right, so here's the urinary system. You have these paired kidneys, and each kidney has a ureter coming out of it that's going to carry urine to the bladder. The bladder is a storage tank, right, for the urine. And then each male and female has a urethra coming out, And we're gonna go over a rebate system, so we go, this is PG-13, right? So nobody freak out when I say body parts, to freak people out, right? But remember, girls have 3 openings down there. If everything's normal, right, we'll go bottom up. Okay, anus, vagina, and urethra is right above the lady's vagina, right? Boys have anus and the urethra going through the penis, so the penis in the male is both reproductive to help deliver sperm to the female and also urination to the urinary system. So it has a dual function. Girl urethra simply to get rid of urine and to do the urinary system function. Okay, pretty cool. But that's gonna need to know. All right, so it went to kidney location, blah, 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 blah. Okay. Now, if you cut a kidney open, it's what we did a couple weeks ago in lab. Remember, there were 3 layers. An outer layer called the cortex, right in here. Then there is the medulla. And then this yellow part is the renal pelvis. Okay, there are 1 million nephrons out here, and we saw those lines. And here's the nephron with the glomerulus, and then the loop and collected ducts. And collected ducts dump into right here the rivers of urine. So these are, we have 1 million little filters of blood that create urine in those yellow tubes. They're not yellow in their body, but they're yellow in the picture, and they all dump into this minor this renal pelvis through these minor calyces. And this is our rivers of urine we make. Okay. Now, you have to draw a nephron, right? I want you to be able to draw a nephron and all those cool things. Here's showing you how the blood comes into the nephron. Look at this. And I forgot to run something out, but nobody emailed me. I told Winston to email me because I've got too much going on. Because I wanted to run off something out of another book, somebody else's book that has all the things in blood and urine. And I just like a table that shows you what's in urine, right? And I forgot to do that at this moment, so we're going to just have to, I'll try to bring it to y'all next week. But you can see the 1, 2, 3, 4, 5 shows the blood coming in. Renal arteries lead to segmental, interlobular, arcuate, then interlobular. Afferent is the one going into the glomerulus. And then the efferent comes out and forms this purple pericubital capillary bed. And that's where all the good stuff gets put back in the blood. So we literally bring the water in. It's like a coffee filter there. Everything small falls through the holes, the slits in the capillary bed. And so water, all the urea, amino acids, simple sugars, amino acids, everything falls through into the filtrate, into the yellow tube. And then as it goes down the proximal coupling tubule, the loop of the nephron, the distal coupling tubule, the collected duct, we reabsorb all the good stuff. A lot of the water is reabsorbed, almost all the sugar, all the amino acids, right? And then we concentrate that urine to where you urinate about 1.8 liters a day. And you normally drink about 1.8 liters a day. So the amount of water intake or liquid intake usually equals urinary output. Pretty cool. But these are little microfilters, these nephrons, which is the glomerulus and the tubing, proximal convoluted tubule, loop of the nephron, distal convoluted tubule, and collected ducts form a nephron. And you have 1 million in each kidney. Okay, now we're going to blow that up and look at it real quick. You can see it there. You see the line, the flow of the urine, the filtrate, which will become urine. So there are 3 steps in making urine. There's going to be filtration, and here it is. Here's an electron microscope at 92,000 power. You can see that these little slits, water and all the small stuff is going to fall through. The blood flows through here, back out here. So water and everything little falls out, goes down the tube. Everything big stays in. The guy. I want you to see something here, really important. Can you see now why people who have high blood pressure, untreated, are going to get what? Kidney failure, right? Because it blows those little capillary beds blow. Just like if I put a water balloon on a water hose, it's going to blow it out, right? And so think about that water hose with little holes in the balloon, but if you turn it up too high, you blow it up. And so one of the big signs of people who have high blood pressure like me is they start having kidney failure. And it blows up these little capillary beds. Okay. All right, and here she's just showing the epithelium lining of all the tubes. Nothing much there, just showing you that they have epithelium lines, everything. And another thing that we were talking about, I think really cool yesterday or Monday, was that the distal convoluted tubule comes back up and touches the glomerulus right here, and what's called the juxtaglomerulus apparatus. And what's going on here is these cells right here called macula densa cells. And these juxtaglomerular cells are monitoring blood pressure coming through here by monitoring chlorine ions, by measuring the number of ions that come out. And if pressure is too low, then these cells produce a compound called renin that is going to get in the bloodstream and then go to the, I'm going to show you a crazy mechanism that involves this activates a chemical made by the liver that's got to go to the lungs to be converted into another chemical that makes a compound called angiotensin II, and that goes to the adrenal gland and makes you make aldosterone, which is our second hormone that controls blood pressure. Remember 88 from the posterior pituitary? That was a big one. Well, the other one is aldosterone from the, and it makes sense. Come on, man. The adrenal gland is sitting on top of the what? Kidney. You know it does something to the kidney, and that's the big hormone it makes that affects the kidney. But along the way, that angiotensin II also causes smooth muscles to contract on blood vessels and raises blood pressure. And that is the known cause of hereditary blood pressure, which I have. And the treatment then is to somehow knock out this angiotensin. And I was telling the other day, I'm going to tell you that I went to the doctor and I knew I from lab, I checked my blood pressure and I knew I would wake up at night and feel my blood vessels, I could feel my heart beating and my blood pressure was high. And so when I went, it was like 150 over 110. And he put me on an $8 pill a month. And I went home and took the pill that one next morning and took my blood pressure. About 3 hours later, it was 110 over 70. That's crazy, bro. He even said, I texted him a picture of it, my doctor, and he said, if it falls below 110 again, take half a pill. I mean, literally, okay? But can you imagine? I mean, I may have already damaged my kidneys because of this high blood pressure flowing through here. But, and he said the thing I think blew my mind is we don't know why the body does that. So they have not figured out why we make too much angiotensin. But everybody, like if you got a family that has high blood pressure, that's 90% chance to cause of it. Pretty wild, if you ask me. Anyway, but it's one of the ways we control blood pressure. We'll see that in just a minute. All right, okay, 2 types of nephrons, 80% of them stay in the cortex, 20% dip down into the deep ones here, these juxtamedullary ones, the juxtamedullary ones. And that actually, these actually make that pyramid that you see in the kidney, make the little loop, makes the pyramid structure. Okay, once again, that'd be a good one to draw. Kidney stones, all kind of nephron problems. Okay, and here are the processes. We'll work away, list the 3 steps in making urine. Okay, we got to have filtration, that's glomerulus, right? Really good stuff. Then we immediately in the proximal colon tubule, we reabsorb 80% of the stuff. And that's why I want y'all to see this table that just showed everything in blood, everything in urine, and then how much is in the final urine. Filtrate at the beginning, what falls through, and then what gets reabsorbed. And we actually see concentration of certain ions, and then of course the reabsorption of lots of water. And I think it's kind of cool. And she doesn't do tables in here. I wish she had. I think that makes it a little bit better. And then the third thing we do is we actually secrete things into the tubules. We can secrete ions and including drugs. If any of y'all have ever tried to work at a bank or at a casino and you're going to be handling money, they're going to ask for a blood sample, a urine sample, maybe even a hair sample. They can tell if you've done cocaine for like 6 months or a year in your hair. There are traces left in the hair from it growing and stuff in it. It's kind of crazy, yeah, for real. But anyway, now usually we would say, and this is what the simpler books would say, you have filtration here, which is the only place it occurs, and then mainly reabsorption, almost all of it occurs right here in the proximal, but we know there's some over here, and then there's a huge amount of reabsorption of water here. This is actually where we concentrate the urine. So I used to teach it like filtration, reabsorption, secretion, and then reabsorption again, right? Because you get a double reabsorption. In reality, reabsorption is occurring all the way through, and secretion can occur in like 3 of the main places. So it's kind of like all the way through. There's the drug can be secreted, and I heard ions can be gotten rid of. Okay, but the 3 processes are what? Filtration, tubular reabsorption, and then secretion. Okay, but I like that she does a little bit more realistic because it's occurring all the way through. Okay, and so we end up with this super concentrated urine here at the end. Okay, and then we talk more about filtration pressure, and I think she loved this. She loves some deep physiology. And I actually showed some of the videos. I'm not going to waste y'all's time. Y'all can watch these videos. They're all in the study area on that chapter online. I watch them. As a matter of fact, I can just sit down and let her teach it to y'all. And she goes over the entire thing and better lecture than I give y'all. Okay, so watch that video. And she actually has 3 of them here explaining how this works. And I showed the last one, I believe, because I thought it was pretty good. Okay, and it talks about filtration rate and pressure here. A lot of issues with that. How much, a lot going on here that can control blood flow through the kidneys and thereby filtration. And I like the little rivers of urine. You can see the little the urine and the electrolytes flowing through the tube. So you're making urine here. That's a good video, especially the last one. All right, and then we will talk about that. The ways we control it. There is a Feedback now, natural auto regulation. But here's the one I was talking about earlier, this renin-angiotensin complex. Okay, and so we're going to produce this renin. I think we have a picture over here. So here's what happens when blood pressure gets low. The jugular glomerular cells, macular dense cells produce renin. It converts a liver protein called angiotensin into angiotensin 1. Now this is OCD. That has to go to the capillary bed in the lung to be converted into angiotensin 2. And look what this does. Causes vasoconstriction of efferent arteriole, making more filter. It's like putting a water hose on the drain of the sink, and the sink's going to fill up. Then it causes, this is where I have high blood, it causes all the arteries in your body to squeeze down on smooth muscle, promotes sodium and calcium reabsorption, thereby water reabsorption, thereby raising blood pressure, and then the production of the hormone aldosterone. And it tells the hypothalamus to thirsty for more. It's a pretty powerful chemical. And the drug I take stops this from binding. So it binds to the receptors, so this can't bind to the smooth muscle, so you don't get this effect, but you get the rest of the effect. So it stops it from binding to smooth muscle. It inhibits the receptor. Pretty crazy. And there's the other one there. You can watch these videos. I'm going to move on. I won't hit that again for y'all because I think it's really important to understand that. Other hormones here, we have one called arterial natriuretic peptide made by the aorta. If you get stretched too much, and that goes and makes you stop, makes you drop urine and go lower blood pressure. Because at some point you're going to blow a valve. You know what I'm saying? If you're having a heart attack and the heart rate is too high. So this will lower blood pressure real quick. Norepinephrine, another one that decreases that. It's going to increase blood flow and blood pressure. That's fight or flight. Okay, so we got a couple of those. Pretty cool how that can work. I'll show you about how that. A little more physiology of that. Here's a nice table showing how we control filtration rate. With this auto regulation, then we have the hormone, and then we have the nervous system. The autonomic nervous system can do that too. Can trigger the release of that hormone. Okay, kidney failure, dialysis, pretty cool. I don't think I have a good picture here of this, but think about this. Here's how dialysis works. It's really, really simple. But it's brilliant. So here is patient. We draw the blood out of their arm, got a little pump that pumps it out, and then it runs it through a tank of basically saline. Okay, with no electrolytes in it. And then a plastic hose runs through this tank. Okay. That has holes in it, just like the capillary bed. And so as it goes through, this saline is pure, nothing in it, very pure. So the ions that go out leave the blood to go into this very very clean, sterile liquid that has no dissolved solids in it. So anything urea and all the other stuff is going to go from what? High and low. So we always continuously replace this fluid nonstop, right? It's always been thrown out. So you're reflushing this through, and all the little bad stuff comes out of the blood, and then we put this right back in your leg. So we literally filter your blood just like a kidney, but on a machine about the size of the palm. But it involves this tubing, the plastic tube, little holes in it, like the glomerulus, filtration. But we use osmosis to things go from high to low. Well, there's stuff in the blood, little things fall through the hole, big things can't go through. The same thing we saw with the glomerulus. But it just takes a long time. You may be on the machine. Anybody got a family member on dialysis? 2 or 3 hours a day, they have to get on this sometimes. Sometimes early on in kidney failure, it's once a week for 2 or 3 hours, but they have to go take a book, bring a phone, bring an iPad, watch a movie, because you're going to be there for a couple of hours sometimes, right? That's how it works. And eventually, though, it will fail. And I made a girl crowd with that. I do not want to upset y'all, okay? But if you got a family member on dialysis, the clock is on. You understand? You cannot live indefinitely on dialysis. And eventually, you got to get a kidney, right? Or you may, I'm thinking 10, 15 years you're going to die at some point, based on how bad your kidneys are going. I have a real good friend of mine that actually taught at DeSoto, one of my very best friends, a really good friend. And he ended up calling me one day, like 10 years ago, and says, look, man, can you teach my classroom with this over at DeSoto? I'm like, well, I can cover it, we'll cover it. And he said, I'm not gonna tell anybody else, but I found out when I was 23, that I have a very bad genetic kidney disease, that I'm gonna have to have a kidney at some point. My sister, we found out she was like 28 and had a kidney. So I've known most of my life that I was going to have to do this, and I'm like, I just really upset me. I'm like, well, can you check me and see when my kidneys will work? He said, I think I got like 5 years to get a kidney, and I'm already like top 5 in Memphis area. And so but he really thought he was going to get one that summer, and he ended up being number 1 for about 2 years. He drove all halfway to Dallas one day to get a kidney, him and his wife, and got a call halfway to Dallas that it was and had hepatitis, and they said it didn't. Someone had died in the car wreck, they had already harvested the organ and everything, and it was no good. Anyway, he ended up getting one, and he actually had, the person had hepatitis. And so he had to take hepatitis medicine, to kill that bad liver killing disease. And so he took that, and he had to just like stay out of, he almost COVID, he was COVID quarantining before COVID, because he couldn't be around anybody. Then as soon as he was able to go see everybody, COVID hit. So I haven't even seen him face to face in 2 years. But he's doing really good. And he was doing dialysis machines and everything, and he had to go in like every other day. It really was going down fast. I say that because this is one of the main killers of people in America. I mean, obviously, heart problems is number one, cancer, but this is like number 3, kidney failure. It's a big, big deal. We need one of you really brilliant people to go figure out a way to make to regrow kidneys, which is I think we're really close to being able to regrow kidneys for people. Okay. And so the drug I take is angiotensin receptor blocker. So here's the one I take for $8. And I have some good advice for y'all today. So when I was seeing my doctor, he's told me, I'm taking him to the Grizzly game tonight because he won't, I'm not going to make you pay for his ticket after he's done so much medical for me. But I did pay my bill with him. But anyway, he made me this, he told me this the other day, we were laughing about this. He said, he got down, he said, I'm going to give you this pill. And this is the one I would take if I had high blood pressure. And he said, if you ever go to a doctor and you're going to have something done, a procedure done, say this phrase to them. What would you do this year? He said, that is a game changer for a doctor, because then it makes them really think about, would I give you this drug or would I take this other drug? So he said, this one has no side effects. Now, I'm telling you, the only thing I've noticed, I've been doing now since December, is I get sleepy at night like quicker than I used to. I fall asleep now about 9 o'clock and I'm waking up at 5 in the morning. I'm not a morning person. This is really weird. My wife is not happy. Because she likes to sleep in, but I can't, because if I go to bed at 11, 9, I'll leave at 6 hours. So I'm ready to go at 5. So I usually go to bed around 12:30 or 1. And I actually fell asleep in my seat Tuesday night watching the Grizzly game. Woke up and it was just like a blue screen and had to back up to if they won. It's not good, right? Getting old. Now I getting old. But isn't that amazing? $8, that's nothing, man. I can blow that. They're going to cafeteria, So I'm just saying, that blows my mind that that something like that can work. But that's the main cause of high blood pressure in America right here. Hereditary high blood pressure, which is crazy. Okay, so we got reabsorption. Okay, blah, 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 blah. Showing how the water is reabsorbed here in these tubules. Okay, now another thing that happens here is we're going to see, don't worry about that, is that we have a huge amount of reabsorption of obviously ions. Look at sodium, potassium, chlorine, sulfate. I'm going to run that table I'm bringing to you. 100% of nutrients are reabsorbed. We did that little chem strip, right? And we're looking for glucose. If you have glucose in your urine, you have diabetes, right? If you have blood in your urine, that means that those capillaries are blowing and red blood cells are falling through. That's not good, right? And you don't have any protein. So if you see any nutrients, that's a problem. 65% of water is refiltered back in and lots of ions, okay? So we got to have a way to move this stuff around. We have active transport of all that in and out. Sodium, potassium, all kind of active transport pulling that out. It's showing us how the things are reabsorbed here. Bicarbonates are reabsorbed. We know about the buffer effect. She gets a little carried away with that. Those aquaporins, those tunnels that water go through, they suck water out of that urine. So what we're going to see is we've got to have a salt gradient in this interstitial space. And let me show you what I mean here. So what I'm talking about is we have to create a salt gradient in here, not in the tubule, but in this space in here, so that when those aquapores open up, the water will run out. Okay. So let's see if that's, I think this is good. We'll watch a little bit of this. Some of these, and I can't do it with the pen, sorry. Let's watch a little bit of this. Cut the pen off. I want y'all to see here.
45 gallons of water and small solutes filter out of the blood and the glomerular capillaries each day. Of course, we don't produce and excrete that amount of urine. This is because 99% of the water and solutes filtered are subsequently returned to the blood by the process of reabsorption. Reabsorption reclaims water and solutes from the filtrate and returns them to the blood. This process can happen by 2 alternative mechanisms: the paracellular route, in which substances pass between adjacent tubular cells, or the transcellular route, in which substances have to move through the tubular cells. Reabsorption can take place via passive transport, such as diffusion or osmosis, or via active transport, which uses ATP. The proximal tubule of the nephron receives the filtrate as it exits the capsular space. The proximal tubule is a site for rapid and extensive reabsorption. Virtually all the nutrients and vitamins that were filtered out of the glomerular capillaries are immediately reabsorbed into the peritubular capillaries. Furthermore, there is significant reabsorption of electrolytes, such as sodium, potassium, and chloride ions, as well as reabsorption of bicarbonate ions, which is critical for pH homeostasis. Finally, about 65% of the water filtered is quickly reabsorbed in this initial section of the tubule. This type of water reabsorption is called obligatory reabsorption. If we pause the flow of filtrate for a minute and focus on water reabsorption, you will see that in the kidneys, water follows solute and is reabsorbed via osmosis, a type of passive transport. Water reabsorption happens via both transcellular and paracellular routes and uses channels called aquaporins. The filtrate is further modified by the process of secretion. During tubular secretion, substances are moved from the blood into the filtrate to eventually be excreted. Secretion always uses active transport and therefore requires ATP. The proximal tubule.
Give a little review to it. Okay, I want y'all to see a little bit slower.
Ions, nitrogenous wastes, and certain drugs are secreted.
Remember, we could change our pH for dumping hydrogen, remember, and raise that, so that's where it does. Anyway, I think it was, maybe that was, what did this time now? I got talking, did it cut itself off? Or did it play through? Thought it was a little bit longer than that.
More than 45 gallons of water and small solutes filter out of the blood in the glomerular
Oh, start it over, never mind.
each day.
Come on, start
Of
over.
course, we
All right.
don't produce and excrete that amount of urine.
Okay, maybe there's another little video. Let's see. Think so, hang on. I'm gonna show it to you, but this is really good. I mean, you can't, this is what I love about the animation. Here we go. So this is the second half of it. But I mean, you just can't be seeing with your eyes
After
instead of me trying to
filtration
stop.
in the glomerulus,
What?
extensive reabsorption and secretion in the proximal tubule, and water and ion reabsorption in the nephron loop, the filtrate reaches the last part of the nephron, known as the distal tubule. The properties and functions of the distal tubule are very similar to those of the cortical collecting duct, so we will discuss them together. In contrast to the preceding sections of the tubule, where water reabsorption is obligatory, reabsorption in the distal tubule and collecting duct depends on the needs of the body and is closely controlled by hormones. Indeed, water reabsorption in the distal tubule is called facultative, which means able to adapt to a need. Two important hormones that control reabsorption and secretion in the distal tubule and collecting duct are ADH, or antidiuretic hormone, and aldosterone. As its name suggests, antidiuretic hormone prevents diuresis, or loss of water in the urine. It is released by the posterior pituitary gland
That
and
second
controls
hormone over
facultative
the blood
reabsorption of water. In the presence of ADH, water channels known as aquaporins are inserted into the membranes of tubular cells to allow for rapid water reabsorption by osmosis, provided a gradient is present to drive osmosis. Aldosterone is a hormone produced by the adrenal cortex, and it promotes sodium ion reabsorption.
There's your
and
two hormones,
exchange of
remember, that
potassium
control blood
ion
pressure.
secretion. Reabsorption of sodium ions also indirectly drives water reabsorption by osmosis. Finally, if necessary for pH balance, aldosterone stimulates the secretion of hydrogen ions. The hormone AMP, which we previously discussed in the context of GFR regulation, inhibits the release of ADH and aldosterone. In conclusion, the distal tubule and cortical collecting duct are responsible for the selective reabsorption of water and sodium, calcium, and bicarbonate ions, as well as the secretion of potassium and hydrogen ions.
Okay, now guys, look, I know this seems like crazy, especially that y'all haven't seen the first video and I'm just throwing that at y'all. But once you watch this a couple of times, I mean, this is actually a fairly simple organ, right? Really, it's just like a coffee machine filter, like making a coffee filter. filtering stuff out, right? And just putting the good stuff back in the blood, throwing the bad stuff back out. I mean, it's really a brilliant organ, right? And here we are, like 2021, and we got a machine that big that can sort of do the job and not take to replace the kids. You cannot live on dialysis forever. Just blows my mind. So a lot of kudos to God on this organ. Super impressive organ. Okay. Now last one. Now this next question on the test. Let's do this for number 6. And look, 25. Y'all can watch last year's video. 25 is 15 minutes at the end of that video that I've already got out there. Okay. But this last question, I missed this one when I took this. Okay. So I always like to ask y'all things I missed. Okay. That's a sign of a bad teacher. Good teachers, I think. Anyway, describe the counter-current mechanism of what does it set up. Okay. Now I'm going to go ahead and quick tell y'all the answer. It's going to set up that salt gradient that allows that water to be sucked out of that collecting duct. Okay. So you're right back in. I won't go back to the video, but you know, it's the very last thing where aldosterone and ADH triggers the aldosterone to open. Something's still got to drive it. And so we set up a huge salt gradient in the interstitial space in between the tubules and the blood vessels. That's why I think nobody want to eat this thing, because it's mega salty. Okay. And you watch this video and it's going to show it. So basically, it's kind of like a perpetual motion machine. It's going to set up salt gradient. Okay. And I want to show you the video. Actually, will probably be better than me trying to explain it. Okay. So what's it? So here's a great summary. Look at that. Money. Look, money right there, right? Look, that tells you everything we just went over. Look, what happens in the proximal tubule, the loop of the nephron, the distal and collecting tubes. Great summary there. And the last thing is this 85% of water's got to be reabsorbed, and we got to have a mechanism to do it. And what we're going to see is we're going to build a salt gradient. And see, those numbers there are called milli equivalents of, and that's a measurement of concentration. Okay. And so look at the numbers in the tubules. I guess I was thinking wrong here, but look, the concentration of ions here is 300 milliequivalents. And look, as you go down, look, it concentrates down to 650, and then it goes back down over here. So we're reabsorbing these ions, right? And see all that salt being pulled out? That creates a super salt concentration out here. And so we get down to where we get only 50 milliequivalents of things in the urine. Okay. So we build this, so we suck all that salt out, and it is going to then pull that water out in the presence of ADH and aldosterone. Notice this says in the absence of ADH, solutes are reabsorbed while water remains in the filtrate. But when that hormone hits it, the aldosterone's open, and the water follows that sodium right out. And that's how we get it down to 1.8 liters a day. Did y'all hear that? 1,500 milliliters per hour being filtered, right? I mean, you tickled yourself to death in just a few minutes, right? If it wasn't for this massive water reabsorption. Okay, and so this countercurrent mechanism multiplier builds up this sodium, and I got a video that shows it. So watch. Sometimes a million words can be explained. There's the actual milliequivalents of concentration, osmotic pressure in the interstitial space. Look, at the top, 300, 400, 600, 900, 1,200, and at the very bottom of this loop, 1,200 milliequivalent, salt loaded. So when that collecting duct comes by, it sucks the water right out. So the countercurrent mechanism creates a salt gradient that allows us to concentrate urine.
After extensive reabsorption of water, nutrients, and electrolytes in the proximal tubule, the filtrate arrives at the
More time, the better.
Let's track what happens to the filtrate as it passes through this portion of the renal tubule.
What's it?
The nephron loops of juxtamedullary nephrons descend deep into the medulla and act as a system called the countercurrent multiplier. Countercurrent simply means that the two limbs of the loop are close to each other and the filtrate in them flows in opposite directions. To help understand how the system works, we'll first focus on the individual segments of the loop. The thick ascending limb of the loop is made of cuboidal epithelial cells. These cells are impermeable to water, but they pump sodium and chloride ions into the interstitial fluid via active transport. As a result, the concentration of sodium and chloride ions in the interstitial fluid increases, and their concentration in the filtrate decreases. Notice how this has created a concentration gradient in the medullary interstitial fluid. The interstitial fluid concentration is about 200 milliosmoles higher than the filtrate concentration all along the ascending limb. This concentration gradient is critical to water reabsorption from the medullary collecting ducts, which we will see in a later animation. Next, let's look at the thin descending limb. It consists of simple squamous epithelium that is freely permeable to water, but not solutes. As the filtrate descends through this limb, water is reabsorbed via osmosis because of the higher solute concentration in the surrounding interstitial fluid. The filtrate enters the loop with a concentration of about 300 milliosmoles, then begins to quickly lose water by osmosis to match the high solute concentration of the surrounding interstitial fluid. Thanks to the continuous loss of water, the filtrate becomes more concentrated as it flows down the descending limb. It reaches a maximal concentration of 1200 milliosmoles at the hairpin turn of the loop. The highly concentrated filtrate that reaches the thick ascending limb then drives more sodium and chloride ion reabsorption.
So yeah, this kind of boots
This is
itself, and
a
that
key
sodium
event
is
because the
gone.
pumps in the thick ascending limb will work only if the sodium and chloride ion concentration in the filtrate is high enough. In summary, sodium and chloride ion reabsorption in the ascending limb promotes water reabsorption in the descending limb, and in turn, water reabsorption makes it easier for sodium and chloride ions to be reabsorbed. Now you can see why we refer to this system as a multiplier. This efficient countercurrent setup allows the two processes to amplify or multiply each other's effects. To see the complete picture, we need to add the vasorecta capillaries. They run parallel to the nephron loop, but the filtrate and blood flow in opposite directions. The vasorecta act as a special kind of vascular system called a countercurrent exchanger. As the vasorecta descend, they pick up sodium and chloride ions and lose water because the blood concentration is lower than that of the surrounding interstitial fluid. By the time the blood reaches the deepest part of the medulla, it has a concentration of about 1200 milliosmoles. In contrast, the ascending vasorecta passively pick up water and lose sodium and chloride ions because the blood now has a higher
That keeps
concentration.
the sodium to the chlorine from being carried out. That allows it to stay
In
concentrated.
conclusion, the countercurrent multiplier and exchange mechanisms of the nephron loops and the vasorecta accomplish two main tasks. First, they efficiently reabsorb between 15 and 25% of the remaining water. And second, they are able to create and maintain a steep concentration gradient in the interstitial fluid of the medulla.
And that's going to be used in this last step. I thought that was the last video. I had looked at these in a little while. And this is going to show the water being reabsorbed by that sodium. And then we'll be done.
In this animation, we are going to combine what we know about facultative water reabsorption with what we learned about the medullary concentration gradient in order to understand how the body produces dilute or concentrated urine. Keep in mind that homeostatic mechanisms are not directly responsible for urine production, but rather for maintaining water balance in the body. However, the amount of urine produced depends upon the amount of water reabsorbed. Remember that water can be reabsorbed in the distal tubule and collecting ducts only if ADH is present and if a concentration gradient is there to drive osmosis. The concentration gradient in the medulla is constantly maintained by the countercurrent multiplier of the nephron loop, urea reabsorption in the medullary collecting ducts, and countercurrent exchange by the vasorecta. Initially, filtrate entering the renal medulla has the same concentration as the interstitial fluid, so no gradient is present to drive water reabsorption. As the filtrate moves deeper into the medulla, the increasing medullary concentration creates a gradient that drives water reabsorption by osmosis if ADH is present. More water reabsorption means less water remains in the filtrate, and therefore a small amount of concentrated
See how
urine
yellow it is?
produced.
Concentrated urine.
In the absence of ADH, no water reabsorption takes place in the late distal tubule, cortical collecting duct, or medullary collecting duct, and therefore more water remains in the filtrate. At the same time, reabsorption of sodium and chloride ions continues, so the number of solutes in the filtrate decreases. In this way, large amounts of dilute urine are produced.
And that's going to lower your blood pressure.
Newly formed urine drains from the papillary ducts to the minor calyces, then from the minor calyces to the major calyces, and finally to the renal pelvis. The renal pelvis then drains urine into the organs of the urinary tract, and from there urine is expelled from the body.
What do you think? Pretty good. I mean, really good videos. They spent some good money, I think, on these and did a really good job there. Okay, and I think that's gonna be about all I got in this chapter, I believe. And so then that's my last question, right? So he creates this, there we go, look at that. It creates a salt gradient that allows us to what? Suck the water, concentrate urine when we need to raise blood pressure, right? In the presence of ADH. These alpha-porins open up, and then the water simply goes to the salt, and you may concentrate, and you don't urinate as much, right? You pull the water out of the urine and concentrate your urine. Pretty cool. There's some tests we can do. We can do, I mean, obviously here's what's normally in urine. We can do urinalysis. We did that in lab, but we can also look for the release of a chemical. And so that they can actually give you a creatine chemical, and it should pass out through your urine within 24 hours. If it don't, then you have kidney failure. So there are chemicals we can put in to see if your kidneys are working. I give you a pill and see if it comes out the other end. And we've already looked, I mean, nothing much here, just the bladder. I would tell one bad kidney stone story. I've got 3 minutes here. So sometimes the kidney stones usually occur in the ureters and the calyxes. But my doctor friend, I mean, someone with the night going to the Grizzly game, he had a brother-in-law who never thought he was worthy of his wife. Okay, they never wanted the night went off. And so this is about 15 years ago. He said he was at the end of the day, and the nurse walks in and says, "You have one more patient, and it's your father-in-law." He's like, "Whoa!" He never comes to the doctor. He walks in doing this, and he goes, "There's something wrong right here. I can't tinkle. I hadn't urinated in like a week." And he's like, "Dude, I don't want to." So in his mind, I don't even want to tell me. So but he went ahead and he could feel a knot down there. He's in urology, and he went on home, sent him on urology, and the next day he comes to work, and the urologist is waiting on him at his desk. He said, "You're not going to believe this. He's coming to your office." He threw an X-ray. He had a stone get down in the ureter and form, and by the side of the marble, and it hung in the urethra, and then he tried to tinkle it out because he is a bad, like army gung ho, just think, John Wayne kind of guy. And he had tried to tinkle it out, and it got stuck in his urethra, and they had to go in with a rotor and cut it up, and then go in and pull it out. And he said that when he'd been in a lot of things, I'd never seen one that big. And he said, and I don't know how many have ever seen them, and I'm sorry, these movies are really not appropriate sometimes. I really thought Off the Power movies were really funny when they came out. Remember the first one, he peed for like 20 minutes? Size 15, just like a minute of it, but it's the funniest thing ever. He just peed for like a minute. He said that's what he did. He said he had been holding it for like a week. He just like never stopped for like a minute. So that's bad, right? Kidney stones right there. So he got down into your urethra. And I'm like, whoa. But here you got your. Yes, it could, but he did say he was dribbling a little bit. A little bit of leakage, but it didn't shut it off. But yeah, he probably could have had really bad kidney damage if he hadn't came on in, but he was like really hurt. And that's why he was walking like that. He had a marble stuck in his urethra. Wow. Yeah. And my mother, I say one more to my mother here. She was having incontinence, inability to control urination. And so we have to literally she has to wear a diaper and stuff and done all kinds of stuff. Good problem for this. She has actually had 2 procedures done. They actually went in and Botox her bladder. And that blew my mind because Botox paralyzes the muscles, right? And I was thinking they were shooting the sphincter, right, which would paralyze it and it would not open or close. What they were doing is a lot of people have irritable urinary bladder syndrome where it just contracts a lot and you pee in your sleep or whatever. So that worked for several years. And then they've done a procedure where they put electric probe in here that comes out her body, that she shocks it to keep it working. And that's up a little bit to work those muscles. But a very bad quality of life if you can't control your urine, right? I mean, think about that. So if we go somewhere, we have to put like plastic covers on the beds and everything, you can't control it. But anyway, so what I was saying is you start out in diapers and you end up in diapers, right? Okay. All right, good stop here. Thank y'all. Okay, look, we're just gonna let y'all look at 25 on your own, ask those 2 questions. They're very obvious in the chapter, and we'll pick up Monday in 26. Okay, 2 chapters to go. Y'all have a good day. Appreciate y'all. Good videos. If you can watch those again, I've thrown